Hello and welcome to the 5th FMSP Core Prerequisites video. These videos are designed to help you get ahead with independent study of the A2 Core, ready to develop the skills in A2 Further Pure modules. This is what you need to know before working through this video. If you're not sure about all of this, work through the relevant videos first. And do note that this video is about developing fluency in the product and quotient rules. It is assumed that you have already been introduced to them. It's a good idea to have all of this ready to hand before you start, so pause the recording now and go and get everything together. It's particularly important with this video, which is developing fluency, that you've set aside sufficient time to tackle the questions as well as to watch the video. If you've not seen the product and quotient rule before, you need to postpone this video until you have. On the other hand, parametric and implicit differentiation we are going to be introducing from scratch, so you don't need to have seen these before. Here's the product rule written informally. Write the first, differentiate the second, plus write the second, differentiate the first. As with the chain rule, we're aiming to be able to do this mentally. So here we go with our first example of a mental method. It may help for you to split the function so you can see the two halves, and then dy by dx is write the first, differentiate the second, plus write the second, but notice that I'm leaving a space there so that I can differentiate the first and write it in front as usual. I can then write that in a factorised form. Here's another example. Again, if it helps, draw a line to separate the two halves. So, write the first, differentiate the second. That's 1 over x, plus write the second, and I'm going to write that at the end, and differentiate the first. Now, is chain rule, so you need to be fluent with the chain rule so that you can apply it in the middle of a product rule question. Is this thing to the power 3, so that's 3, and that to the power 2, and then differentiate what's in the bracket to get 5, so I need to multiply that by 5 to get 15. That's one of the reasons why you need to be really good with the chain rule. Okay, fluency with the quotient rule is nothing like as important. The formula's in the book and you just need to make sure you can use it reliably. Sometimes it's easier to rewrite the quotient with a negative power and use the product rule. Here's an example of where you need to use the quotient rule and how you need to be quite confident with it. Tan x is sin x over cos x. So dy by dx, I've got the quotient rule up there because it's in the formula book, so you don't need to memorise it. V is the bottom one, so we put that down squared, and then you write the denominator, which is cos x, and differentiate the numerator, so differentiate sin, I get cos again, so that's cos squared. Take away, write the top one, which is sine, and differentiate the bottom one, which differentiate cos, and you get minus sine. So that gives me sine squared and changes that to a plus. Cos squared plus sine squared, of course, is 1, so that's 1 over cos squared, which is sec squared. And this result is in the formula book. The derivative of tan is sec squared. Okay, let's check how we're getting on with these. Pause the video and have a go at this yourself, mentally, without showing working, before looking at the solution. Okay, let's have a go. There are my two halves, x squared and 2x plus 1 to the 4. So, write the first, differentiate the second. That's 4 times 2x plus 1 cubed, and then differentiate in the bracket. That gives me 2, so instead of 4 that will be 8. Plus, write the second, and notice that I'm leaving space in front of it, and differentiate the first, differentiate x squared, and I get 2x. I can tidy this up a bit because I've got all those x's and 2x plus 1's to different powers. So I've got an x in both of them, and I've got a 2x plus 1 cubed in both of them, and I've got a factor of 2 in both of them. So what have I got left for the first term? Well, I need a 4 and an x, and that's all. And for the second one, the 2x is out the front, so it's just the 2x plus 1. So that's 2x times 2x plus 1 all cubed times 6x plus 1. Okay, one more for you to have a go at, so pause the video and try this one. Okay, it's usually best to rewrite square roots as fractional powers, so that's x 2x minus 3 to the half, and you might want to draw a line in there to split the two sections. So, write the first, differentiate the second, so that's a half 2x minus 3 to the minus a half, and then differentiate in the brackets. That will give me 2, so I don't need that half. Plus, write the second and differentiate the first, which is just 1, so that's nice and easy. Okay, now tidying this up so it looks like one of those things that we've got as options. I clearly need a new denominator of 2x minus 3 to the half. So let's do that. Okay, if we look at the first term, I've got 2x minus 3 to the minus a half, that's there, and an x. For the second term, I need 2x minus 3 to the half, and I've got 2x minus 3 to the minus a half. So I'm going to need 2x minus 3, just check that. 2x minus 3 over 2x minus 3 to the half will be 2x minus 3 to the half, so that's correct. That gives me 3x minus 3 on the top, and root 2x minus 3 on the bottom, and I can factorise the top. And there we go, it's answer C. Now there was plenty of working in that, but the working was in the tidying up, not in doing the actual differentiation. Okay, that's enough of product and quotient rules, though we will be coming back to them later on. Parametric functions. A parametric function is one where both y and x are defined in terms of another variable, often t or theta. So here's an example, x equals 3t and y equals t squared plus 1. What we can do is to use a table of values of t to find x and y pairs. So here's an xy pair, minus 9, 10, and another pair and so on. I'm going to start with this one for plotting, 0, 1. And then the next one is 3, 2. And if you look at the other side, I've got 3, minus 2. And then 6, 5, and then 9, 10. It's going to look something like this, and you can see that it is a parabola, slightly wobbly line. Okay, alternatively I can use simultaneous equations to eliminate the parameter and get myself an expression just in terms of x and y. So here we go, x equals 3t, y equals t squared plus 1. It's usually, but not always, easiest to solve these by substitution, and from this I get from the first equation that x over 3 is equal to t, and I'll substitute that into the second one, y equals x over 3 all squared plus 1, and my equation is y equals x squared over 9 plus 1, and you can see that that is indeed what I sketched. Parametric differentiation is basically just the chain rule. If I want dy by dx, I need to do dy by dt times dt by dx. And sometimes dt by dx will be easiest to work out, sometimes dx by dt, in which case we'll need that division sign in there. So here we go. I've got x equals t squared and y equals t cubed. So dx by dt is 2t, and dy by dt is 3t squared, and therefore dy by dx is dy by dt divided by dx by dt, so that's 2t, sorry, dy by dt first, 3t squared divided by 2t, or 3 over 2t. I'll do another example. X equals cos t, y equals sin t. So dx by dt is minus sin t, and dy by dt is cos t. Chain rule tells us that dy by dx is dy by dt divided by dx by dt. So that's cos t over minus sin t, which is minus cot t. Do take care with these, make sure that you get all the t's down. Okay, now it's your turn. Pause the video while you have a go at this one. Okay, let's see if you got the right answer. So we'll start by differentiating those two functions, this time with respect to theta. It becomes increasingly important that you are very careful about what variable you're working with, which variable you are differentiating with respect to. That becomes even more important in the next section, so make sure you're getting it right now. Differentiating x with respect to theta, the 4 disappears and 2 cos theta becomes minus 2 sin theta. Differentiate y with respect to theta, the 2 goes to 0, and differentiate 2 sin theta, and I get 2 cos theta. Whoops. dy by dx is dy by d theta divided by dx by d theta, and that is 2 cos theta over minus 2 sin theta, which is minus cot theta again. So that's A. Pause the video again while you try this.